All right, section 2, we're going to deal some more with these exponential functions. In section 1, what we did was we simplified expressions involving exponents and radicals. Now what we're going to do is look at functions. So we're actually going to have the y equals piece. And how we know something's an exponential function is because my x is in the exponent. Okay, that's how we recognize exponential functions. And when we get into logarithmic ideas, it's important to understand, okay, what situation do I have? Where's my variable? How am I going to get it out of that spot? So 2 things we're going to do today is, 1, we're going to graph. Second thing is we're going to deal with equations that involve those exponents. So when we look at an exponential function, we have y, or we could have f of x equals a times b to the x. Okay. I like to look at a and b every time. Okay, so on that first example, I had y equals b to the x. If I have y equals 2 to the x, I always want to put an a value out there. A lot of times it'll be 1 with what we're dealing with, because a is going to be our start point. Okay, my start point is where I start my graph. Well, obviously, if we go to the left, we keep going to negative infinity, so there's no real start point, but we talk about our start point as my y-intercept, or the value I get for my y or my f of x when my x is 0. Okay. Second thing, we were going to talk about my b value as my rate of change. Okay. Rate of change in linear situations is what I added every time I took one more step to the right for my x direction. Here's going to be what we multiply by each time. Okay, so an example of a couple of situations. 1, we could have growth or decay when we talk about exponential functions. Exponential growth, it starts out getting bigger slowly, and then all of a sudden it takes off. And examples, if I have a calling tree, I call 2 people, each of those, each of those people call 2 people, and so on and so forth. So I start out with 1, increase by 1 to 2. Those 2 call 4, so we increase by 2. Those 4 call 8, so we increase by 4. So the rate that we're increasing at is constantly getting larger. Okay, decay, things get smaller. Okay, half-life. Half of something decays away over a certain amount of time, then another half. And again, one of the things that we want to look at a little closer is that it's going to get closer and closer to 0, but not quite get there. So it's going to create an asymptote situation. Okay, so a couple things. If we go in and look at some of the characteristics, 1, domain. Okay, it's going to be all real numbers. Okay, and it doesn't matter if it's growth or decay. So you notice there's 2 situations. This is growth when my b value, when my rate of change is greater than 1. Decay is when my value for b, my rate of change, is somewhere between 0 and 1. Okay, now we don't have negative values. If we did that, we'd bounce back and forth across the axis. But my domain, my x values I can use, I can plug anything in for those, so all reals. My range, notice, like I said, we're going to have a situation where my y's are always going to be greater than 0. We don't get to 0 again, like I said, with our decay. It gets closer and closer, doesn't get there. If I looked at the growth situation and went to the left, it gets closer and closer. The example I always talk about with decay also is that if I let you line up at the wall and go halfway to the door, every time the second hand hits 12, okay, one of the things that, excuse me, is that you'll never get to the door. You'll get closer and closer, you just won't quite get there. Y-intercept, what I'm going to do is change that a little bit, okay, because I'm going to use it as my start point, so I'm actually going to call my y-intercept 0, whatever that value for A is. Okay. Horizontal asymptote, so we're going to talk about horizontal asymptotes in here. Okay, it says the negative x-axis, but remember, we talk about asymptotes as a line. So our asymptote here is going to be y equals 0. We're getting closer and closer to 0. And so we're going to look at it that way. We're not going to worry about vertical asymptotes because there isn't one. Okay, so if we look at a few things here quickly, when I graph something like y equals 2 times 3 to the x, I want to look at A and I want to look at B. Now, what I do is I use this table here all the time. Okay, reason being is I'm going to start with my parent graph, my A and B pieces, and my parent graph changes depending on what B is every time. Okay, so I want to redo this every time, and then if there's some transformations, we'll deal with that. So what I do is I start with 0A, so 0, 2, because we talked about my start point. Okay, my start point again is that y-intercept. Okay, and then we talked about how b, my 3 here, is my rate of change. So when I take a step to the right, okay, I'm going to multiply by 3. So 2 times 3, which is a times b. Okay, so I get 6. Okay. Now, again, if we go the opposite direction, we do the opposite operation. So now what I'm going to do is take, instead of multiplying by 3, I'm going to divide by 3 when I take a step to the left. Okay. Now, like I said, one other thing we're going to deal with is my y-intercept. My y-intercept is equal to 0. Okay, or y equal to 0, I'm sorry. And I'm going to draw that line in. Okay. Now, we'll get to a couple examples where we'll have those transformations like we had earlier. So now I have my points, and again, I like to start at the middle one because I go through the one on the right by increasing and go through this one, just get closer to the axes, or my asymptote, I'm sorry. Now, second thing we should recognize that, hey, this is growth, and so my graph should look like growth, which it does. All right, so now we've added 4 to it this time. Okay, so I would still start with just this parent piece and get my value for A, get my value for B, get my value for A divided by B. Okay, I would also think about my horizontal asymptote. And I think I wrote that down wrong back here, so just in case you need to change that, that's your horizontal asymptote. I apologize. Okay, I'm going to start with y equals 0. And what I want to think about is, what does that 4 do? Okay, now, when we dealt with our transformations earlier this year, we talked about inside and outside. Inside this time is going to be inside my exponent. And if it's inside my exponent, that's going to change my x value. So this 4 is outside, so this is going to change my y value. And so what I'm going to do is I'm going to add 4 to every one of these. Okay. So this goes to 4 2/3, this goes to 6, this goes to 10. But I'm also going to add 4 to my asymptote because it's a y. If I change my x, it's not going to affect my asymptote. So I'm going to move my asymptote up 4. Okay. And then I'll plot my new points. At -1, I'm at 4 2/3. At 0, I'm now at 6, and then 10. Okay. So if you notice, it's truly the same graph as the last one, just slid up 4 units. Okay. Now, another situation, yeah, that's a reflection over the x-axis. Okay. But I don't deal with that as a separate transformation. I'm going to deal with this now as my value for A. So my start point is -2. I'm still going to take A times B, and I'm still going to take A divided by B. Did nothing to my y, so my horizontal asymptote is still at 0. Okay. Plot my points. And as you see, just like on that earlier one, it's truly just that first one reflected over that x-axis again. All right, now here's an example of decay because my b value is between 0 and 1. Don't get in the idea that if I have a fraction in there that it's going to be decay, because if I had y equals 3/2 to the x power, that value is greater than 1, so that would make it a growth situation. Still the same thing. Here's my A, here's my B. Okay, so A is 3. 3 times 1/2 is 3/2. A divided by B. 3 divided by 1/2, again, multiplied by your reciprocal, equals 6. Okay, so -1, 6. Okay, then we get 0, 3/2. Oops, sorry. We get 0, 3. 1, 3/2. Always want to look at that horizontal asymptote. It's just y equals 0. Sketch it in. What it looks like in this case is simply a reflection over the y-axis from that original. Okay, but again, it's decay, so I expected it to get closer and closer to my asymptote as we went left to right.